Okay, any questions on this derivation? Well, this is always true. This expression is always true. If you have a wire, then this is the magnetic induction you have. If you have a volume charge density, then you should just replace this I dot dl by j times dv. But this is always true in magnetostatics. This will not be true when we study magnetodynamics. This is true only in statics. Just a warning. We said that B can be written in this form also. J cross R minus R prime divided by R minus R prime cube times dV, where this J is some volume current density. And we know that J can be written as rho times the velocity at that point, well, the velocity of the charges at that point. Now, if we have a point charge, then rho would be just the Q times the Dirac delta, let's say R minus R0 times V, let's call it V0. We have a particle at the point R0 at this time, at a given time. It's at the point R0. It has a velocity V0 at that time. Now, if you put it back, B will be equal to mu0 over 4 pi Q Dirac delta R minus R0 times V0 cross R minus R prime divided by R minus R prime cube. Let me just put the prime also over the V because we are integrating over the coordinate R prime. This is at the point R prime. This is at the point R prime, Dirac delta R prime minus R0. Now, if you just carry out this integral, B just becomes mu0 over 4 pi Q times V0 cross R minus R0 divided by R minus R0 cube. You can, in some books on magnetism, you can see that this is the expression for the magnetic field of a point charge, which is not true. This is not the correct expression. Because you see, the problem is the Biot-Savart law is valid in magnetostatics, which means the charge density should be independent of time. But in this problem, since rho is equal to Q times Dirac delta R minus R0, hence d rho by dt is non-zero. Because since the particle is moving, R0 is constantly changing, and hence the charge density at a given point is constantly changing. So this is not a magnetostatic problem, and hence this expression is not correct, strictly speaking. It's only approximately true that magnetic field of a moving point charge can be written in this form. Now we will see next semester how to calculate corrections to this one, and we will see that this expression is true, but the corrections to this term is proportional to the speed of the charged object divided by the speed of light. So as long as the charges are moving at speeds much slower than the speed of light, and this is a good enough approximation. Yes? Now, in statics, we are saying that, okay, the the system should not be changing in time, But nevertheless, we can ask, okay, if the system is changing in time slowly, then what are the corrections? For example, this system, we have this point charge moving, and hence the change in the system is proportional to the velocity of this charge. Now, velocity has a unit. We cannot say that the velocity, the speed is large or small without comparing to some other unit. We have to compare it with something else. And it will turn out that we need to compare the speeds in our system or the changes in our system with the speed of light. If the changes happen slowly compared to the speed of light, then that system we can approximate as a magnetostatic system. For example, even the electricity that we use, although the frequency is 60 hertz, it's constantly changing, it's changing 60 times a second, it is a good enough approximation for magnetostatic. I mean, if you try to calculate the magnetic field of this wire, you can just use the magnetostatic approximation and it will be a good enough description. Because the speed of light is really a huge number compared to the speeds here. Now let's do another application. Let's assume we have a ring that is carrying a current I. Again, the system is not changing in time. At least in this reference frame, it's not changing in time, so we can use the magnetostatics. So the question is, what will be the magnetic field at this point? Let's say at a height h from our ring. This is a circle with radius r. Now we will again use the fact that dB will be equal to mu 0 over 4 pi times I dl cross r minus r prime divided by r minus r prime cube. Now let's take a segment over here. This is my dl. So what is the direction of the magnetic field, the contribution to the total magnetic field of this segment? dB, what is the direction corresponding to this dl? So this is our dl, or let's say dl. This is my r minus r prime vector. So the dB will be in this direction. This is my dB. This is perpendicular. This is also perpendicular. Do you agree that this is also perpendicular over here? You see, this is my dl. This is my dB. Or this is my r minus r prime. So this angle over here is also 90 degrees, no matter what h is. Now I can take the diametrically opposite segment. This is my dl. This will be the corresponding distance. What will be the direction of that dB? Let's call it dl prime. Well, dl prime is somewhat pointing towards you. This is my dB. This is my r minus r prime. So dl cross r minus r prime is somewhere in that direction. This is my dB prime. This angle is again 90 degrees. But dB, observe there is no integral over here. The magnitude of dB. What is the magnitude of dB? Let's say this length is small r. It is just dl r over r cube Sine of the angle between the two, what's the angle between the L and r minus r prime vector? Or let me just call it, sorry, let me call that capital D. What is the angle between r minus r prime vector and dl? 90 degrees, sine of 90 degrees, 1. But it is also the magnitude of dB prime. dl prime has the same length as dl. It is at this distance, since I'm at a point along the central axis, every point on my ring is at the same distance from this point that I choose along this axis. So d is the same for this segment. D is the same, dl is the same, I is the same. The angle between this dl prime and this r minus r prime for that segment is the same. So the magnitudes of dB and dB prime, they are exactly equal.
Hocam bu dB şöyle değil mi? Şurayı şey olarak düşünürsek şöyle şu şekilde mi? Şu arkaya doğru mu?
Which dl?
dB.
dB. Let's say this is my ring. I am at the point at the center. This is the direction of the current is running in this direction. So here, this is the direction of dl. This is, I'm looking, let's say, the magnetic field at this point. This is my dr. So this dl cross this r minus r prime is a vector in that direction. Yeah. Something like this. So if I look at the segment over there, then it will be in this direction. But then what I did was, this is my ring. I get a dl over here in this direction, another dl over here in the opposite direction. One creates a magnet, one contributes to the total magnetic field in this direction. The other one contributes in that direction. When I take the sum, their horizontal components would be equal because they make the same angle and they have the same magnitude. So the sum will be in the z direction, vertical. So the total magnetic field created by this system will be vertically up. Let's say this is the z-axis. B is in the z direction only. The horizontal components, they will cancel. Which will be equal to, let's see, I have mu 0 I over 4 pi dl times dl over d squared. This is the contribution, the magnitude of the contribution from this segment. If I calculate the z direction, the z component of this one, let me call this angle theta. I have to multiply with cosine theta. This gives me, multiplied with this cosine theta, this gives me the z component of the contribution from this segment over here. But then let's say I'm just summing over all these segments. As I calculate the contributions of those segments, mu 0 is the same for all, I is the same for all of them, 4 pi is the same, d squared is the same, cosine theta is the same for all of them. So I can just take them out of the integration sign. Times the integral of dl. But dl is nothing but the length of those small segments. And when I sum them up, I get the total circumference of my ring. So this becomes mu 0 I over 4 pi cosine theta over d squared times 2 pi r. Now let's look at cosine theta. You see that angle over here is theta. So this angle over here is 90 minus theta. But that tells me that this angle over here is also theta. So cosine of theta is R over D. Let's see, what is D? So let's come back over here. This is equal to mu 0 I over 4 pi times 2 pi r over d squared. Cosine theta is r over d. So the total, this is in the z direction. So the total magnetic induction of this ring along its axis is just, let's cancel these 2 pi's, 2 mu 0 I pi r squared divided by 2 pi d cubed in the z direction. Well, I didn't cancel these pi's. Now, if you are very far away, then D is approximately H. So this is mu 0 over 2 pi I pi r squared divided by h cubed in the z direction. Well, go back in your notes and look at the electric field of a dipole along the axis of the dipole. They basically have the same form. So that is why we will be identifying this thing, I times pi r squared. This is a loop with an area pi r squared. This is the magnetic dipole moment. Well, we will study this multiple expansion in the magnetic field case also in more detail later on. But this is just a place where we see this magnetic dipole moment. Any questions?
Hocam yukarı çıkabilir misin? Bak burada cos theta nereden geldi? İntegralini aldığımız için mi?
Now, you see, here what we said, the total magnetic induction is in the z direction. Why? Because if you look at this diagram, we said that each segment of this loop will contribute a magnetic field dB, which has a horizontal component and a vertical component. But when we sum them up, the horizontal components, they will just cancel each other. So we will be left with the vertical component only. So I don't need to worry about the horizontal components of this dB, because in the integral they will just cancel. I only need to worry about the vertical components of dB. Now, if you look at this dB, it makes an angle theta. This is my dB. It makes an angle theta with the z-axis. So to calculate the z component, I have to multiply dB, its magnitude, by cosine theta. That cosine theta just gives me the z component of the contribution to the magnetic induction. Well, the next is the quadrupole. We have the dipole, then we have the quadrupole, octupole, etc. We don't have the monopole. In magnetic field doesn't have a monopole. In the electric field, you have the monopole, dipole, octupole, etc. In this case, there's the monopole is 0. It's the dipole, octupole, etc. Let's look at the force between two straight wires. So let's say this one carries a current I1, the other one carries a current I2. First, let's calculate the force acting on the first wire due to the second wire. Now, since the second wire is exerting the force, first we have to identify the magnetic field created by the second wire. Now, what is the direction of the magnetic field created by the second wire at the position of the first wire? Yes, if you can just take a small segment. We are looking at the magnetic field at that point. So this is our dl. This is the position vector of the observation point. You have to take the cross product of dl with r. It is outward. You can also use your right-hand rule in a different way. Just grab the wire such that your thumb points in the direction of the current. Then your fingers curl in the direction of the magnetic field. So the magnetic field is created by the second wire is into the screen here. It is out of the screen over on the other side. So at this point, the magnetic field, along the first wire, the magnetic field created by the second wire, let's call it P2, is out of the screen. And let's say they are separated by a distance d. Now, what is the magnetic field? What's the magnitude of P2? Well, we had calculated it. This is the magnetic field created by an infinite straight wire carrying a current I. So it's mu0 I divided by 2 pi times the distance. Well, in this case, mu0, the current that is creating this B2 field is I2 divided by 2 pi times d. This is the magnitude of the magnetic field that the second wire creates. Now let's look at the force acting on the first wire. Remember, the force acting on a segment of wire, it was written as I times dl cross b. In this case, we are taking a segment in the first wire, so let's just call it dl1. And we are not looking at the total magnetic field, we are only considering the magnetic field created by the second wire. This is the F12, the force acting on the first wire due to the second wire. First of all, what is the direction of this force? What is the direction of dl1? dl1 is upward. B is in that direction. So dl1 cross B is towards the other wire. Convinced?
Yani akımın yönünü niye tersini düşünüyorum?
No, I mean the definition of dl vector is it is tangent to the wire and it is in the direction of the current. That is how we define these dl's.
Ben mesela QVB gibi düşünürsem,
Okay.
elektronlardan
Well, let's look at from the electrons. Then you are saying that their velocity is downward, magnetic field is in this direction, V cross B is in this direction. But we are multiplying it with a negative number, which is the charge. So the force acting on an electron is still towards the other wire. Well, to avoid these complications, we are always treating the current as if it is the motion of positive charges. So this is the force, this is the direction of the force. So we can write this as I1 times mu0 over 2 pi d times I2. Let's say this is the x, this is the y, this is the z-axis, z direction. In the x direction, times dl, dl1, or the force per unit length. The total, if it's an infinite wire, the total force will be infinite, but we can still talk about the force per unit length of the wire. It will be 1 over 2 pi d times mu0 I1 times I2 in the x direction. Now, what is the direction? Any question up to this point? Well, the total force is infinite. So I can only, in fact, since ideally I'm taking infinite wire, the force will also be infinite. But then I can still talk about the force per unit length. By the way, this is just a constant along the wire. So if, for example, you are interested in the force acting on a given length of a wire, just multiply this number by that length. Now let's do it the other way around. The force acting on the second wire due to the first wire. So what is the direction of B1? The magnetic induction created by the first wire at the position of the second wire. Not the same. Not even the magnitude is the same. The currents need not be the same. So we can say this is B1. And the B1 will be mu0 I1 over 2 pi d. It is in the minus z direction. What is the direction of the force acting on the second wire? Okay, B1, the magnetic field is into the screen. What is the direction of DL? DL is upward. What is the DL cross B? So this is my DL, this is B, DL cross B. It's in this direction, towards the other wire. So this is F21, in the -6 direction. It's in the -6 direction. I2 times the B1 is mu0 I1 over 2 pi D times DL2. And again, the force per unit length is equal to, in the -6 direction, mu0 over 2 pi D I1 times I2 in the -x hat direction. Which is, by the way, minus the force acting on the first wire due to the second wire. Which is something we expect. I mean, they have to be action-reaction pairs, Newton's third law.
Hocam, waylar kendi yarattığı manyetik alandan da etkilenir mi?
In this one, no. Before this coming to that problem, let's look at this problem again. So let's say let's assume I1 is equal to I2 is equal to 1 ampere. Their separation is 1 meter. What is the force per unit length? The magnitude. Well, if you say mu0 over 2 pi, I will say it is wrong. It doesn't even have the correct units. So it is 4 pi times 10 to the power minus 7 Tesla meters divided by 2 pi times 1 meter. One meter squared. So dF by dL would be equal to 2 times 10 to the power minus 7 newtons per meter.
Metrekare mi hocam?
Oh, sorry, it's just a meter. And let's see, and ampere squared. Yes, now it's correct. So let's say if D is equal to not 1 meter, but let's say 1 centimeter, dF by dL would be just 2 times 10 to the power minus 5 newtons per meter. By the way, this is the definition of the ampere, how you define an ampere. You use 2 wires, you make sure that they carry exactly the same current. You measure the force per unit length. They are separated, let's say, by 1 centimeter. Once the force per unit length is equal to this number, then you know that the current running through those wires is 1 ampere. Usually we define the coulomb in terms of the ampere. 1 coulomb is the amount of charge that passes through a point, through a given point, provided that the current is 1 ampere. Because ampere is easier to measure than coulomb. Let's do another example of the calculation of the magnetic field and the calculation of the force. Let's assume we have a single wire, but this time it is bent. Let's say at 90 degrees, and it carries a current I. Now, what will be the direction of the magnetic field created by this segment at the position of this segment? Well, let's say it's pointing, this is the direction of the current. Wrap your fingers around, so it's pointing, your fingers is pointing outside. So at this point, the magnetic field will be outside. Of course, this is the magnetic field created by this part of the wire. Now let's say, what is the direction of the force acting on this wire? You see, dl is pointing in that direction. B is in this direction. So dl cross B is downward. This is the force the direction of the force acting on the lower part of the wire. Now, what will be the direction of the magnetic field in the vertical segment created by this part of the wire? Wrap your fingers around such that your thumb points in the direction of the current, so it is pointing again out of the screen. What is the direction of the force? This is the direction of dl. This is the direction of B. dl cross B is in this direction. Do you see any problem in these directions of the forces? No problem. What happened to Newton's action-reaction pairs?
Actually, when the current I is passing like this, itself has a magnetic field which is toward the inside the screen, so it cancels out the magnetic field behind.
No. Just a short answer.
Manyetik force için reaction'dan bahsedelim.
Let's do another example. Maybe, as your friend points out, in this case, there's something weird happening at this point as it's bending. Let's go back to our previous. Sure.
This magnetic field is due to this current, right?
Okay.
And also, this current has a magnetic field which is inside the screen, so it cancels out this one. Can you say like that?
No. Because you see, the force that this wire will feel will be only due to the magnetic field of the other one. Because otherwise, if this feels a force on its own, then what do you do?
So does
it move?
The magnetic field of this wire have any effect on the magnetic
Sure, but you see, just like in the case of the electric field, if I'm a point charge, you are another point charge, the force that I will feel will be only due to the electric field created by you. I will not be able to exert a force on myself. Otherwise, I would have been in trouble because the electric field that I create at my own position is infinite. Just like this one. You see, at this point, let's just take this point to be very, very far away. It is so far away that this segment of the wire doesn't even create a magnetic field over there. But since I'm very close to this wire, the magnetic field created by this wire would be huge on its own, without the contribution of this one. So there is no such cancellation. Anyway, even if there were a cancellation, it doesn't really matter because this wire will not be, nothing can exert a force on itself without violating Newton's third law. Of course, assuming we would like to live with Newton's third law. Let's go back to a different problem. Well, it's related. This moves with a velocity v, this moves with a velocity v prime. And assuming they are moving slow enough, slow compared to the speed of light, we can use our previous approximation that the B field created by a moving point charge will be given by V cross R over R cubed. QV cross R over R cubed, where this R vector over here is the position of our observation point where we are measuring the magnetic field relative to the charge. We said that this expression is not completely correct. There are corrections to it, but as long as the point charges are moving slowly enough, slow compared to the speed of light, that's a good enough approximation. Now let's come back to this one. What is the direction of the magnetic field at this point created by this one? You see, this is my V vector. This is my R vector. Okay, this is the R vector. This is the V vector. So R cross V. No, V cross R is outwards. So this is the direction of the B, created by the charge moving with velocity v. What is the force acting on it? This is the general expression of the magnetic force. V, B, V cross B is in this direction. Right? What about this one? What is the direction of the magnetic field at this point due to this one? Outward or inward? You say V prime is in this direction. This is R. V prime cross R is inward. What is the direction of the force? This is V, this is B, V cross B, upward. Again, there is no action-reaction pair. There is no Newton's third law. But if there is no Newton's third law, we don't have linear momentum conservation. I don't care about the angular momentum for the time being. I'm worried about the linear momentum. There's no linear momentum conservation in my system. Well, in this case, what will happen if I just would put a hinge over here and allow my system to move, these wires will open up. Well, as they open up, this gains a linear momentum in this direction. This gains a linear momentum in this direction. So my whole system is gaining a linear momentum in this direction. So linear momentum again is not conserved. So there doesn't seem to be any linear momentum conservation here. Well, that is something we will answer next semester, unfortunately. Now, there is this observation. Keep this in mind. We are kind of having problems with Newton's third law. We already mentioned the problem with change of reference frames. You see, Lorentz force depends on this velocity, which changes as you go from frame to frame. This is some peculiarity on magnetic field. So Newton's third law seems that it is not valid, and hence we don't have linear momentum conservation in systems that have magnetic force acting on them. We didn't have this problem in electrostatics. The forces were always opposite to each other. They always formed action-reaction pairs. But here not. So this will be resolved in electromagnetic theory 2. So any questions except on these one? Well, as of today, just in the break, I checked that there were only 2 students asking for recitations. You can, of course, still vote for a recitation until midnight. I will check in the morning. If there are sufficient requests, we will have a recitation, but I don't think there will be. Yes, I don't think we will be able to continue doing recitations after the first midterm. So see you on Friday.